Hey everyone, welcome to the first contest in the ACSL. This is one of the concepts you're going to need to know for ACSL Contest 1, which is computer number systems. So I'm going to go through the concept of computer number systems in this video, and in the next video I'm going to go through some problems or examples that you might see on the ACSL and how to tackle them. So in this video, let's figure out what a computer number system is. So these are the four different number systems that you're going to need to know for the ACSL. Decimal, binary, octal, and hexadecimal, and each of them has a different base, and that's what makes it a different number system. So first we have the decimal number system, which is the system that we use regularly. So this is a base 10 system, and it uses the symbols from 0 through 9 to represent its numbers. So this is obviously the number system that we use the most, so we're already pretty familiar with it, and we're going to do our first example with this to figure out what we mean by a base system. Next off, we have the binary system, which is a base 2 system. You might be familiar with it. It only uses the two symbols 0 and 1. Next, we have the octal system, which is the base 8 system. This one is pretty rare. You don't really see it much, but it's one of the required number systems on the ACSL. So the base 8 system uses the symbols from 0 through 7. And if you count those symbols up, those are 8 symbols. Remember, we always start with 0, so count 0. Next, we have the hexadecimal system, and this is a base 16 system. You may not be familiar with this one, however, hexadecimal system is usually used when we're expressing color values on the color spectrum in computer science. So this system uses symbols 0 through F. So the last six numbers are represented with the values A through F as its symbols, and we'll look at an example of that quickly at the end of the video as well. Okay, so firstly, let's start off with how did we get to base systems anyway? So let's look at an example with the decimal system. If we take the example of the number 128, this number in decimal has three different place values, as we know. From elementary school, we would split up each of these place values. So 8 would be in the first or the ones place, so 8 times 1. And then the 2 would be in the tens place, so 2 times 10, sorry. 2 times 10. And then the 1 would be in the hundreds place, so this would be 1 times 100. Now, if we added all these values up, we would get 100 plus 20 plus 8, which would give you 128. However, in the base system, or how we're trying to think about it here, we can actually go a step further. So we can see that each of the multipliers here is increasing uh, by a factor of 10. So we can express this exponentially. Instead of saying 8 times 1 or 2 times 10, we can say 8 times 10 to the power of 0. You can see we use the base 10 since we increase it by a factor of 10 each place, and we can put the exponent as the index at which that value is. So in this case, 8 is at the index of 0. So this is index 0 since it is the first index 0 since it is the first value in the number. It is in the ones place. So we always start with 0. Next, we would have 2 times 10 to the power of 1, since it's the first index, and then 1 times 10 to the power of 2, since it's in the hundredths place. So you can see that the base is 10, and that never changes. And that's why we call this a base 10 system, since each place increases by a factor of 10, and we simply increase the exponent at the top to register which place that we are trying to talk about. So if you add all these numbers up, we get the same value, 128. So now that we know that, let's try to figure out how to calculate the base values of other number systems. So first we have binary, which we know is a base 2 system, and it only uses the symbols 1 and 0. So in binary, let's say we have a number 101. So how do we calculate what this is in decimal? Well, let's get our first index value, which is 1. We'd multiply this times the base, which is 2, since we're in the binary system, and then we exponentiate 2 with the index, which is 0. So we would get 1 times 1, which is 1. That's the value at that place. Next we have a 0, and this 0 is in the second place, or the first index, so it'd be 0 times 2 to the power of 1, which would give you 0 as the value. And then the last number is 1, so it'd be 1 multiplied by 2 to the power of 2, since it's at the second index, with a base 2, since that stays constant, and 1 times 2 to the power of 2 is 4. Now if we added these values up, we would get 5 as our resulting answer. So 101 in binary equals 5 as a value in decimal. So you can see how we calculate this value from each of the different place values. We simply just put the base, so we multiply the number with the base, and then we put that base to the power of whatever index the value is at, where we're calculating it. So the other systems are now pretty self-explanatory to figure out. We just simply put those numbers with a base of 8 or a base of 16, respectively, for octal and hexadecimal. Another skill that you're going to need to know for the ACSL is how to convert decimal to binary, octal, and hexadecimal, and how you jump between these number systems. For example, how do you jump from binary to hexadecimal, and how do you interchange those values? So those kinds of sort of tips and tricks I'm going to show in the next video where we do some problem examples. Okay, so for our first set of examples, we're going to go over how to go from binary, hex, and octal to a decimal value. So if you're given a value such as this is 256 in octal, as indicated by this base here, how would you convert this to decimal? So we went over this briefly in the other video, so just to review, we start by breaking it up into each of its parts, so 2, 5, and 6. And then from there, we multiply each of the numbers by their base and place value. So in this case, this 6 would just equal 6 times 8 to the power of 0, since it's the first number. And you continue to the left. So 5 times 8 to the power of 1. And then this would be 2 times 8 to the power of 2. And now you just have to add these three numbers together after you calculated their value, and that would be your decimal value. So 2 times 8 to the power of 2, this equals 2 times 64, which is 128. That would be added to 5 times 8 to the power of 1, which is 5 times 8, which is 40. And that would be added to 6 times 8 to the power of 0, which is 6 times 1, which equals 6. So at the end, 128 plus 40 plus 6 is the answer, and this equals 174 when you add it together. So this is how you would find your decimal value from an octal number. All you have to do is break it up into its parts and multiply it out with the correct base value. So you could do this with hex and binary as well. You just have to use 16 and 2 respectively for the bases instead, and then multiply and add in carefully each value to find your decimal value. Okay, next up we have to go into how to go from decimal to these values, and so how to convert from the base 10 system to the other ones. Okay, so for the second example, we have to go from a decimal number to a binary number. So to do any of these conversions from decimal to the other number systems, we have to constantly divide this number and then find the remainders of that number. So we start with the value 18, right down here, and what we do is we divide this with 2. So we constantly do this and find the remainder, and that's going to be the number value in our final value for the binary number. So we start by dividing these two numbers, and obviously we get 9 with a remainder of 0. So make sure you keep those remainders and those solutions, because we need to continue with the next. So then we divide the solution to the first division again with the base, which is 2. So since we're converting to binary, we're dividing with 2. If we were converting from decimal to hex, for example, we would be dividing with 16 instead, and with octal we would be dividing with 8. So if we continue this division, we would get 2 times 4 with a remainder of 1. We go yet again, 2 times 2 with a remainder of 0. One more time, 2 times 1 with a remainder of 0. And then here, you can't go into 1 any more times, so it would just be 2 times 0 with a remainder of 1. and we stop there. So now, to get our final binary number as our solution, what we would do is we'd go from the top all the way down to the bottom and put all of our remainders together. So in this case, it is 1, 0, 0, 1, 0, and this would be the binary representation of 18 in decimal. So this is how you get from decimal to any of the other three number systems. So just remember to divide by the base value of that system, and then keep dividing and putting all the remainders together at the end. Okay, so the last thing you're going to need to know is how to convert between octal, hex, and binary. So to do this, what we do is we break up these octal and hex numbers into bits of binary, and then put those together to form our answers. So, for example, if we look at this chart, we can see that all of the octal numbers, they go all the way up to 7, which is the maximum for any one digit in octal. And for that number, the binary equivalent is 111. So that is the maximum that a binary number can reach within 3 digits. So we represent each octal digit with 3 binary digits. Then if we go down to hexadecimal, we can see that the maximum value is f, which would be 15 in regular decimal value. So f, that is equivalent to binary 4 digits of 1. So we represent each hexadecimal value in bits of 4. So using this knowledge, we can go ahead and very easily convert any octal or hex value to a binary value, simply by looking at each digit and then translating it to the binary equivalent of that digit. So if we look at this value, 274, in octal, to convert this to binary, we just look at each digit, so we start with the 2, and we convert that to its binary equivalent. So octal is represented in bits of 3, so we can take the 2 and look at the chart. We can see that in octal, 2 is equivalent to 10 in binary. You don't have to memorize this chart. Just make sure you know the value of the octal or hexadecimal value in decimal, and you can always convert. So for example, we know that in octal 2 equals just 2 in decimal, so we can just easily convert 2 to binary with the process that we just learned in the last clip. So here, 2 would translate to 10, and in a bit of 3 it would be 010, because the leading 0 doesn't matter. And from there, we move on to the next, 7, which translates to 111 in binary. And then 4, which translates to 100 in binary, as seen here in the chart. 100. So, if we put all of this together, we can pretty easily see that 274 in octal equals 010111100 in binary. And you can also remove this leading 0. I was just there to help you think about it, but this would be the answer at the end. Okay, so that was pretty simple, and for hex it would be the same, but we would just use bits of 4 instead. So we could just look at this chart. So for example, if it was 89A, the answer would just be 1000, 1001, and then 1010. And that would be the final binary number if that was the hex number you were looking at. Alright, now how do we convert between octal and hex? Well, in that case, we also use binary bits to help us. So for example, if we wanted to convert the same number, which was 274, from octal to hexadecimal, first we would convert it again into binary. So let's convert this back to binary. Let's look at the chart again. We started at 10, and then the 7 would be 111, and then the 4 was 100. So this was in binary. Now we just have to convert this binary value to hex. So to convert a binary value to hex, or octal for that matter, we just have to break up the binary value into 4 or 3 bits. So in this case, since we're going from binary to hex, we have to break up the binary into bits of 4. So if we look at this, we start from here. So this would be a bit of 4 right there, and this is another bit of 4 at the end. So these two would be the values of our final hex value, 1011 and 1100. So these two are the bits that we would translate to hex. So the first one, 1011, if we look at our chart, it is B in hexadecimal, and 1100 is C in hexadecimal. So this equals BC in hexadecimal. So you can see that we just simply have to break it up into its separate bits to find out our final value. Now, just as a quick review example, since we just went from this octal value to the binary value, can we convert it back accurately? So let's just do that really quick. If we start with this value as the binary, to convert back to 274, what we need to do is break this up into parts of 3. So if we start breaking it up, we can see pretty quickly that the first or the last two numbers are only 2. So we can keep it that way, or we can just add a 0 at the end for convenience. So that would be a bit of 3. And then we would write those 3 bits down, 1 0 0 1 0, 1 1 1, and 1 0 0. And then we would just refer to our chart again, and we can pretty quickly see this would just become 274 in octal. So that's how you would convert from octal and hex to binary and between those 3. So make sure you learn this. It would be very helpful if you memorize this chart. You don't have to. Again, you could just know that a hexadecimal value equals a certain decimal value and then convert back to binary. But it is always useful to know this chart if you can. And yeah, hopefully that helped, and make sure that you study up on this because it's especially helpful on the ACSL exam to know these tips and tricks for this part especially.